Hey guys, BuildZoid here, and today we're going to be doing another motherboard PCB breakdown. This time it's the Gigabyte Z790 Aorus Elite AX, and this board is exactly the same as the regular Aorus Elite without the AX, because this just tells you that the board comes with this Wi-Fi add-in card. That's the only difference between the AX and non-AX version of this motherboard. Anyway, this board was provided to me by Gigabyte, so big thank you to them for sending it over for testing. And with that out of the way, let's get into it. Starting off with some of the more noteworthy connectors that you get internally on this board. You get 4 M.2 slots. This first one is connected directly to the CPU, and that runs PCIe Gen 4 by 4. And then these three are connected to the chipset. These are also all PCIe Gen 4 by 4. However, one of these shares its PCIe lanes with 2 of the SATA ports. So you can have 4 M.2 devices and 4 SATA devices, or you can have 6 SATA devices and 3 M.2 devices. You can't have all of them at the same time. There's just not enough bandwidth in the chipset to do that. If you want more details on like how the bandwidth is allocated from the chipset, you can always check the motherboard manual. Anyway, for actual like properly full-size, PCIe slots, we get X16 Gen 5 directly connected to the CPU right over here. Not really all that useful because the only thing you can really put into it is a GPU, unless you want to like give up all of your GPU performance for like high-speed storage, which I guess if you were building some kind of like dedicated storage system with this motherboard might make sense, but most people like to have their GPU connected directly to the CPU because running a GPU through a chipset, especially off of an X4 slot, tends to not be great for performance. Speaking of PCIe slots connected to the chipset, on this board you get 2 of them. Both of them are X4, but this first one is Gen 4 by 4, and the second one is Gen 3 by 4. So the second one is basically just slower. And other than that, you also get a internal USB Type-C header. So if your case has a front panel USB Type-C port, you have the connector for it on the motherboard right there. Anyway, so that's sort of the noteworthy connectors that you get internally on this board, and it's pretty standard Z790 motherboard stuff. Yeah, like I guess if you compare it to B650, this has more connectivity options, but the like max bandwidth is lower because you can get B650 motherboards where I think at least the first CPU slot is always Gen 5, or at least almost always Gen 5, because when you're running the PCIe Gen 5 lanes a short distance, it's not too much of a problem. But yeah, like I think just in terms of general use, like I think this is better in terms of connectivity than most B650 boards because like you just have more connectors and they're more flexible in terms of what they do. So anyway, let's move on to the rear I/O. Where you get a whole bunch of USB Type-A, which I am a big fan of because I am a sucker for USB Type-A ports. Probably why Gigabyte has started like cutting down the audio section for the sake of making more space for USB Type-A ports, but well, I don't care about onboard audio, so I'm totally cool with that. Like, honestly, if these went completely missing, I still wouldn't notice. But anyway, yeah, so there's a bunch of USB Type-A. You also get Wi-Fi 6E over here. There's a USB Type-C port over there. There's 2.5 gig Realtek LAN, and then you do get the cut-down audio section, but you do still have an optical output for the audio. So if you have like an external DAC that uses a optical connection, you do have the connector for that. So, I like this rear I/O. Like I mentioned, I'm just want USB ports, and anything else is just kind of, well, I mean, I do use networking, so though my home network is 1 gig, so I'm kind of indifferent to the 2.5 gig thing, but yeah, basically it's just like I need networking ports and I need USB ports, and everything else is secondary, but depending on your needs, like that depends on what you need from your motherboard. Also, you do get some display outputs for the iGPU, a display port, and HDMI. Anyway, let's move on, back to the internal functionality of this board and go over some sort of more overclocking-oriented features, starting off with the least overclocking-oriented one of them, which is the Q-Flash Plus button over here. This allows you to update the BIOS of the motherboard without even having a compatible CPU. I don't really see that as being particularly helpful on a Z790 motherboard, as Intel's like not going to be releasing 14th gen CPUs on LGA 1700. Like that's not a leak. That's just how Intel works. Every 2 generations you get a new socket. So I don't really think that we're going to see any like CPUs that won't like any new CPUs for this platform. Therefore the actual like real purpose of this kind of gets defeated by that. However, you can sometimes use this to recover from corrupted BIOS flashes. So like if you flash the BIOS and the power goes out and then the BIOS flash doesn't complete correctly, you might be able to recover from that with the QFlash Plus button, though that's not its intended purpose. Anyway, so you do have that, and there's a little LED to indicate that it's actually functioning. Certainly doesn't harm anything, and it's nice that this is just a sort of standard feature on motherboards these days, because I mean, with Intel boards, it's not really an issue, but on the AMD side, you do actually get, like, CPU updates on the same socket. Imagine that. But anyway, or, like, you get CPU upgrades on the same socket. So, yeah. Anyway, let's move on to some more actual overclocking functionality. You get troubleshooting LEDs. No postcode, though, even though there's a suspicious empty space right here. Where certain other motherboards have postcodes, but not this one. But you do get some troubleshooting LEDs. Unfortunately, these are all the same color, and they are right next to each other. So when the board inevitably, like if you screw up your BIOS settings and it gets stuck on some part of the boot process, figuring out which one it's stuck on is probably going to require pulling out the motherboard manual or like covering up one of the LEDs so you can actually read the inscription, like read the silk screen under it. I really wish Gigabyte would at least color code them. Because, yeah, figuring out which part of the post sequence you're in is not great when they're all the same color and all right next to each other. I guess they could have also maybe, like, spaced them out around the board a bit more. Like, they could have tried spacing them out a bit more. Though I'm glad they're not doing that. Like, this was a thing back in the day with motherboards where instead of having all of the, like, boot sequence LEDs right next to each other, you would have like a CPU LED somewhere near the CPU socket and a DRAM LED somewhere near the memory sticks, and that's worse because like you know it might get covered up by heat sinks and stuff. So this I really wish this was just color coded, right? Like that would help a lot in my opinion for making this easier to tell what it is that you're stuck on. But oh well, not the end of the world, especially considering one of the other features that this motherboard has that, in my opinion, basically just, yeah, pretty much just negates the fact that, like, the LEDs are kind of hard to tell what's wrong. There is a clear CMOS button here for some reason. I don't know why. And the reason I don't know why is, like, this makes sense on, like, a test bench motherboard. It doesn't make sense on what I would consider a normie motherboard. And especially because of where this is. Because the thing with the clear CMOS button is, like, if you put this motherboard in a case, like a normie, and it doesn't want to post, and you need to clear the CMOS, you're going to have to take off the side panel to reach that button. But here's a kicker. If you have, like, a high-end modern GPU, I bet the GPU will cover up that button, and so even if you open up the side panel, you're still not going to be able to reach it. Yeah, so I really question as to why they bothered to even include this. There's a clear CMOS jumper down here, right? Like you can just short out this header. So if you want to clear CMOS that way, if you wanted to, you could wire that up to your reset button on the front panel of your case, and then you can do that without even having to take off the side panel. However, the button doesn't hurt anything by being here. I just have no idea what it's doing on a motherboard that like is almost never, like, obviously I've used it on a test bench, but outside of reviewers, I don't think it's ever going to see test bench use. Anyway, this button, on the other hand, is a lot cooler, because this is the multi-key button, and basically, with this button, so the only function you really need to know that this button has is safe boot. And on Intel motherboards, Gigabyte's safe boot works really well. It's incredible. So the first thing, like if you're planning to do a lot of overclocking with this board, basically what you should do, the first thing you do when you go into the BIOS is you go over to the miscellaneous section in the advanced mode, and then you set your multi-key button to safe boot. And then if you screw up your memory timings or your voltages, or for whatever reason you punch in settings that prevent the system from posting, you can press this button. and it will go into the BIOS with all of your garbage tier settings that don't work, but at stock settings. It'll get you in, like, basically, you don't have to clear CMOS to get back into the BIOS, even if you screw up your settings. So this is super helpful if you're doing a lot of memory overclocking, if you're, like, experimenting with termination settings or really anything. If you're experimenting with any memory overclocking settings whatsoever, you're eventually going to get to the point where regularly things don't post, or even going to start at the point where things don't post, depending on what exactly you're trying to do. And in those scenarios, like this button just, you don't need to clear, you don't need to save profiles, you don't need to clear the CMOS, you just press the safe boot button and you're back in the BIOS, all your settings are there, you can go fix whatever mistake you made. It's great. Like, and the best part is, like, Gigabyte seems to be shoving this this button onto basically all of their motherboards now. And yeah, on their Intel boards, this button works amazingly well. I love it. Like, I am just, this is basically the main reason to get a Gigabyte motherboard these days, in my opinion, is this button right here, because it makes life so much easier if you're, experimenting with various overclocking things. And there's also a header next to it. So if you did want to wire this up to your reset button on your, like, front panel, you can, right? Like, yeah, so if you, like, basically if you just want to extend the reach of that button, you can totally do that. You can just wire it to your front panel. Yeah, that's that in terms of sort of the overclocking functionality on this board. And basically, this is the main reason to consider the motherboard, in my opinion, is that button, because it makes memory overclocking so much easier. And actually, really, any kind of overclocking so much easier. Like, if you're pushing your settings to the point that things don't tend to post always, this saves you so much time. Anyway, let's move on to the power delivery on this board. You do get dual 8-pin power connectors, and if you are going to be pushing a 13900K or KS, or maybe even the 13700K, you're going to want to plug in the extra 8-pin power connector. Though, it is worth noting you can technically just plug in half of this power connector. Like, it's designed to do that. That's why your, like, 8-pin, like, most power supplies will have an 8-pin power connector that can split into an 8-pin, like, into two 4-pins. This connector is designed to accept just a 4-pin if necessary. But more realistically, like, if your power supply has an extra CPU power cable, it's going to be an entire extra 8-pin. I've never seen a power supply where you get an 8-pin and a 4-pin. That's not a thing, at least in my experience. Like, either your power supply only has one 8-pin, in which case you probably don't want to be pushing a 13900K to its limits. On the stock power limit, it's fine. It's just like if you're manually overclocking a 13900K, you wouldn't want to just use the single 8-pin power connector, because the 13900K is very, very thirsty, assuming that you have enough cooling. If you don't have enough cooling, then you'll probably run out of cooling before the power connector starts being an issue. But yeah, so if you're really gonna push a 13900K or a 13900KS, plug in both of them. And if you have anything like less than that, like a 13600K, the single 8-pin is more than enough. Like, it's not going to have any issues. So yeah, and Gigabyte is using the high current variant of the 8-pin power connectors. These are solid metal pins, not folded metal pins. So these connectors can easily handle north of 400 watts, assuming your power supply can also deal with that. Which is why, like, some power supplies you might want, like, if you have the option to plug in the extra 8-pin and you're pushing a 13900K to its limits, you should. There. That's the simplest way to think about it. If you don't have a 13900K, you probably don't need the second 8-pin. So, when I say pushing to its limits, I do mean manual overclocking. I guess if you enable multi-core enhancement and the power limit gets set to disabled, the extra 8-pin will also be handy. But yeah, like, if you have the lower core count CPUs, the extra 8-pin really isn't necessary. Anyway, let's talk about the actual power delivery components. So, the way this is, and I'm like, this doesn't do anything. It's just annoying for me to highlight. Anyway, this down here is the VCC in rail. We'll get to what that does eventually. Up here we have one phase of iGPU, and the rest of this is all vCore. Anyway, the controller for vCore and the iGPU rail is this chip over here. And that controller is an on-semiconductor NCP81530. And this is the, like, basically the first motherboard I've ever seen using an on-semiconductor VRM controller. I've seen motherboards with UPI Semiconductor, International Rectifier, Chill, Renesas, Intersil, ST Micro, Rich Tech, but not onsemi. And that's not because like onsemi is like a subpar brand or something. Like onsemi is usually used on GPUs. And yeah, I've never really seen them on motherboards. So like they're really common on like higher end Nvidias. Also, well, just really common on Nvidia GPUs in general, as well as some AMD GPUs. So yeah, I'm kind of surprised. Like interesting that like I haven't seen more motherboards use on semiconductor VRM controllers, but this one does. This is a 8+2 phase controller, and Gigabyte is running it as a 8+1 because nobody cares about the iGPU. We don't need 2 phases to power it. And by nobody cares, I mean I don't care, and I'm the only person that matters. Anyway, moving on. So yeah, you get your 1-phase iGPU. And then 8-phase vCore. Now, in typical modern motherboard fashion, we do have more power stages per phase than just one, right? So each phase is made up of 2 power stages. So like these two chips right next to each other, those are both in the same phase. And basically, what's going on is you have one PWM signal from the controller, and it just hits both of the chips at the same time. So they switch on and off at the same, like to get in sync with each other. And the reason this is done on modern motherboards is that it's a really cost-effective way of basically the thing is, so here it's literally doubling the current capacity per phase, but technically there's nothing stopping you from putting 3 power stages onto the same PWM line, which Asus likes to do a lot, or even 4, which I've also seen Asus do. So yeah, there's really there is an upper limit, but that upper limit is so high that I don't actually know what it is, because at some point your PWM signal would probably just not be able to drive all of the different power stages you've hooked up to it. But the point when that happens is like not a real world concern. Anyway, so yeah, 1 PWM signal going into 2 power stages, because this is a really cost-effective way of doubling your current handling capacity without, like, it doesn't increase the complexity of the motherboard basically at all. And then the only thing you kind of need to do is increase your inductance the inductance of your inductors. Because when you do this, the inductors basically act as one inductor in power. Like, it actually really doesn't behave any different than when they have 2 inductors on one switch node in a like discrete MOSFET-based VRM. So yeah, just a really common thing to do by motherboard manufacturers these days to double your current handling capability. And for the actual power stages, Gigabyte has opted to use on-semiconductor FD. And the funny thing is, like, on-semiconductor power stages on motherboards, that is totally normal. It's just on-semi controllers that are, like, a rare thing, which is kind of interesting. Like, there are tons and tons of motherboards with on-semiconductor power stages and MOSFETs, but controllers, for some reason, have always been, like, a GPU exclusive thing, and so yeah, I found that really surprising to see this controller here. But anyway, these are on-semiconductor FDMF 5062 70 amp smart power stages. And yes, that's a Fairchild Semiconductor part number, and the reasoning for that is very simple. On Semiconductor bought Fairchild Semiconductor a couple years ago. I don't really remember when it was exactly, but anyway, like, OnSemi is still using those Fairchild Semiconductor part numbering schemes for some of their components. Anyway, yeah, so 70 amp smart power stages, and because we do have 2 of them in each phase, and this is an 8-phase, there is 16 of them in total, which means the current handling capability of the VRM itself is very high. So anyway, let's talk about theoretical efficiency for this VRM, which includes the power losses in the power stages as well as the inductors. And I guess I should have mentioned the inductors on this board are 400 nanohenries, which is a rather high-ish inductance, but for a parallel power stages design, it actually makes perfect sense, because having less than like 200 nanohenries per phase gives you a lot of switching noise on the 12-volt side of the of the VRM. So if you had like a 16-phase controller, you would probably see like 150 to like 200 nanohenry inductors because each phase is independent. But if the phases are, or if the power stages are parallel like this in each phase, you use twice the inductance because when both of your high side MOSFETs turned on, your inductors end up being in parallel, and it effectively looks it basically behaves like a 200 nanohenry inductor. Anyway, which doesn't really tell us how much current can flow through these, but unfortunately I don't know what the specs on these are. Generally speaking, inductors are not the current handling bottleneck in a VRM because they're basically a very fancy piece of wire, so they don't really get that hot. So that's why I tend to kind of ignore them in PCB breakdowns. Also, getting specs for them is a massive pain, so that's the other reason. Anyway, output voltage of 1.2 volts and a 600 kilohertz switching frequency. This VRM should be able to output 200 amps of current to the CPU while producing only about 16 watts of heat, which is a very good result. And if this was an AMD motherboard, I'd be telling you about how this is massive overkill and it doesn't even need a VRM heatsink. Unfortunately, this is not an AMD motherboard, and the 13900K is very thirsty. So 300 amps output current, the VRM would be should produce only about 26 watts of heat from the power stages and the inductors, and this is still a good result, but well, we'll get to the sort of asterisk of this board's VRM actually being good soon enough. Anyway, 400 amps output current. So now we're talking you can hit this on custom water cooling, this current range, 200 to 300 amps. If you have a big custom loop, you can definitely pull that much current with a 13900K. It's not really that difficult. Well, it's very hot, but it's not really that difficult to hit that level of current draw. It is hard to cool it, but not that hard to get there. Anyway, 400 amps output, the VRM would produce about 38 watts of heat. And basically at 300 amps, you already very much need a heatsink. The basic rule of thumb is if your power stages are producing, actually, this would technically not need a heatsink if the board was thicker. Because okay, 1 watt of heat per power stage, you can get away with not having a VRM heatsink at that point. But yeah, once you start, approaching almost 2 watts per power stage, you really start needing a VRM heatsink. And then once we get into the sort of extreme overclocking territories of current draw, well, the funny thing is, if you're actually running a Intel CPU, if you're running a CPU on LN2, you're probably not running it in extended loads. And VRMs, especially when they take up this much space on the PCB, do have a decent amount of thermal mass to them. So it takes a while for the temperature to get really hot. But anyway, 500 amps output current, the VRM would produce about 51 watts of heat. So technically, you could do LN2 overclocking with this. You probably wouldn't be able to run Prime 95 constantly on LN2, but nobody does that, so that's not a real concern. Now, the bad news about this VRM is that, yes, we have 16, 70 amp smart power stages. They can handle the current draw of a 13900K, even with a manual static overclock, just fine. Even if it's running Prime 95 small FFTs or some other very high current draw load. The issue is this board uses a 6-layer PCB. And that's sort of the main difference. That's the other big difference between this and, say, a lot of AM5 motherboards is AM5 motherboards almost universally use 8-layer PCBs, and that actually significantly helps with the power losses in the power plane as well as the ability of the PCB to spread heat out. This being a 6-layer PCB runs into it's kind of a funny problem where the VRM itself actually runs less hot than this area of the power plane. And the reasoning for that is obvious. If we look at the back of the board, right, you can very clearly see how the vCore power plane basically narrows down into the CPU socket and then comes in through sort of this area. And so basically when you're pulling, 200 amps, that 200 amps all has to sort of basically squeeze into the socket like that. And that means the VRM itself, that actually runs at acceptable temperatures, even with no airflow, sitting horizontally on a test bench, which is not ideal for the heatsink design on this motherboard. The VRM sits at like 90 degrees Celsius. However, this area of the power plane ends up hitting like 110 degrees Celsius if you have no airflow over it, because, well, that's ultimately where you have the sort of highest current density through the power plane, and this is just a 6-layer PCB. So the power plane does end up getting rather hot. Now, the good news is this was in a zero airflow, stress test, like not realistic whatsoever. If you have the motherboard in a case, it really shouldn't get that hot. But yeah, this is not like we have in terms of MOSFETs, this really shouldn't have any issues powering a 13900K. But then when it comes to the actual copper carrying that current from those MOSFETs to the 13900K, the board has a bit of a bottleneck because it is just a 6-layer PCB. There's just not that much power plane here. And it is a 2-ounce copper PCB. Like, the internal layers are on the double thickness copper, but it's still just 6 layers. Like, yeah, there's not really much you can do about it. This area of the power plane does tend to get very hot on this board if you don't have any airflow, and you're absolutely hammering a 13900K. I don't really consider that a, practical, realistic concern, because, again, if you have any airflow, the power plane will run at acceptable temperatures. But if you don't, yeah, this area of the board ends up getting very hot. Also, keep in mind this is constant 100% load with the CPU pulling well over 300 watts. If you have anything less than a 280 millimeter AIO, you're not going to be able to sustain this kind of power consumption for extended periods of time. So, yeah, I don't consider it a real, I don't consider it a real negative, but it is worth noting, yeah, it's a 6-layer PCB. It just doesn't deal with very high levels of current draw that well. And there's not really a good solution to this as far as I'm concerned, because the VRM itself runs cooler than this area of the power plane, right? It's well, you could have the board have more layers, and then the board is significantly more expensive because PCB layers are not cheap. Yeah. So it's kind of the reason I bring this up is because technically this VRM is not really massive overkill, because the power plane is kind of a bottleneck is basically a bottleneck for the current handling capabilities of all of the MOSFETs and inductors combined. Which, there really isn't anything else to say about that. In terms of, power stage selection, component selection and just VRM cooling, the board does a good job. And then it's just well, it's a 6-layer PCB. There's really nothing that can be done about that in terms of oh yeah, this area of the PCB ends up getting very hot. So anyway, yeah, that's the VCore VRM's current handling capability. And again, if you have any airflow over the board, any airflow, this really shouldn't be a problem. It's just one of those things yeah, don't try to run it passive at high load. That's a bad idea. Anyway, the iGPU phase uses a on-semiconductor NCP 2155, and that's a, wait. Oh, yeah, 302155, and that's a 50 amp DRMOS component. So the difference between DRMOS and smart power stages is not the fact that these are rectangles and this is a square. You can get square smart power stages as well. But basically, smart power stages integrate things like temperature monitoring, current monitoring, and a bunch of safety features. This might have a thermal flag. It definitely doesn't integrate current monitoring, and that's the main difference there. Is just this is a much simpler power stage component with less built-in functionality, and that's why we call it DRMOS, because you have your driver and your MOSFETs, DRMOS. Whereas smart power stages, the power stage part is basically the driver MOSFET bit, and then the smart part is where you have the like current monitoring, temperature monitoring, over temperature protection, over current protection, and there's a very long list of various features that you get with the extra S in front of the power stage. Anyway, yeah, so that's the iGPU VRM. There's like it's a 50 amp power stage. It's going to power the iGPU just fine. Like all people really use the iGPU for is like video encoding. So, uh, and some people don't use the iGPU at all. If you have a F SKU, you don't have an active iGPU, in which case this will literally just sit idle. Anyway, let's talk about the VCCN VRM, which isn't optional because your CPU will literally not function without it. This is controlled by this chip over here, which is a Monolithic Power Systems MP 2940, and that's a two-phase controller from Monolithic Power Systems, and the chips it's controlling are, surprisingly enough, not from Monolithic Power Systems. These are NCP 3160s, and these are 60 amp smart power stages. And the thing is, VCCN is just a 1.8 volt rail that goes to the CPU and powers things like the system, powers the integrated voltage regulator, which then generates power rails like the system agent power rail, the CPU VDDQ power rail, and those are basically minor power supplies for like memory controller and system agent stuff. So this really doesn't have to output a whole lot of current. Yeah, like the two 60 amp smart power stages for this are like more than enough power delivery for VCCN. So nothing to complain about there. Though it is, actually I think it's a different 60 amp smart power stage on the higher end Gigabyte boards, I think. Or it might be a 90. It doesn't really matter. Like memory controllers don't pull that much power. Or like the system agent also doesn't pull that much power. So anyway, that's the VCCN. So yeah, in terms of like current handling capability, this VRM basically, like, you do need some airflow because of the power plane, but other than that, it handles a 13900K without really any issues. In terms of voltage regulation, it also does a very good job. I've measured it with the oscilloscope. Your ideal LLC settings are going to be medium or low LLC, which is expected. That's about the same level as like level 4 on Asus, which is usually where Asus motherboards also get their best voltage regulation. Oh, I guess I should have mentioned, right, so we have the 400 nanohenry inductors, and for output filtering or like bulk capacitance, we have, why is this not in my notes? Okay, we'll flip the board over because, oh, I can't see the power end of the power plane. Oh, well, too bad. Anyway, these are all 10,000 hour. The issue is, I'm pretty sure these two belong to the iGPU. It shouldn't be just one. And then I think actually, it looks like that it's just one for VCCN, which makes, I guess that makes sense. VCCN isn't going to be seeing massive transient loading. Anyway, these are all 10K, like 10,000 hours at 105 degrees Celsius. Nichicon FP caps. So, yeah, FP caps from Nichicon. So these are solid polymer capacitors, which also means like that 10,000 hours at 105 degrees rating, that's not a lifespan. That's just like after this period of time, they degrade by a predetermined amount. It really, like, it's actually not a concern. Like, I like, polymer capacitors don't really die. That's one of the reasons why they're so popular these days, is just they are extremely robust. And that's why you see them anywhere where the voltage requirements allow. And speaking of voltages, these are 6.3 volts. And they're 560 microfarads. And just eyeballing it, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe 11. I think it's probably just 10. Yeah, but 10 or 11 of them for vCore. The thing, and they are through-hole capacitors, but like I mentioned, like, I've actually measured the voltage regulation of this board, and it does a good job. Yeah, like at low LLC, there's no measurable undershoot on the back of the motherboard, by which I mean like right here. Oh, and for the actual filtering directly behind the CPU, we have just a whole bunch of multi-layer ceramic capacitors, along with this 330 microfarad tantalum polymer capacitor. Now, these actually do have limited lifespans compared to polymers. Not like super, again, not super concerning. They don't have like a catastrophic failure. Well, if you don't put them backwards and you don't intentionally massively overload them or overheat them, they don't have catastrophic failure modes. But like if you misuse a capacitor enough, you can basically, if you misuse any component enough, you can get it to explode. But yeah, generally speaking, like any type of like solid capacitor, be that solid like tantalum polymers or aluminum polymers, generally very, very robust. Like they generally don't have catastrophic failure modes unless you like misuse them in some way. Anyway, yeah, the voltage regulation on this board is really good, so I don't really have any complaints for that. And yeah, that basically covers it. Like, the main concern I had when I saw this controller was like, oh, this might have different load line calibration programming compared to other Gigabyte motherboards, because that is a thing, even with other manufacturers. It's not just Gigabyte. Like, depending on which VRM controller is used, you might get completely different load line calibration behavior. And I gotta say, like, to my surprise, this is actually very similar to other Gigabyte Z690 and Z790 motherboard in both terms of like how much VDroop you get at each LLC level, as well as in terms of the voltage regulation behavior. So yeah, good job to Gigabyte on the voltage regulation of this VRM. And for input filtering, we just have 6 270 microfarad, 16 volt FP caps again, which is kind of a lot of input filtering, especially in this price range. There's some other, there's other motherboards in, I think, this price range where you might only see 4 of them. The thing is, the input filtering really isn't anywhere near as important as the output filtering, because this side does have to actually deal with the transients directly from the CPU, whereas the input filtering deals with a sort of tamed version of what the output filtering side sees, because any big current draw spikes have to go through the inductors first. Oh yeah, it doesn't hurt anything to have extra input filtering, though. I mean, yeah, it doesn't hurt anything. It also doesn't really like improve anything in my experience. Anyway, that's pretty much it. Oh wait, I didn't talk about the memory topology. Let's get to that. So it is a daisy chain topology, as you can clearly see from this label right here. Actually, there are T topologies that have a skew towards one set of DIMM slots, but we'll just pretend those don't exist. This is a daisy chain topology, and like I mentioned earlier, this is a 6-layer PCB. So I guess we'll finally put the layer count on the board, 6 layers, which, fun fact, if you want to check the layer count on a Gigabyte motherboard, they have a little indicator usually down in this corner. On this board, it's this right here. Actually, I wonder if on the back we can actually see the little 6. No, we can't, because that area is in darkness. Good job, me, with that photo. Anyway, yeah, but this is a 6-layer PCB with a daisy chain topology, and Gigabyte QVLs it up to 7600. The thing, I would not recommend that you try 7600. My experience has, like, depending on how good your CPU is, even 7200 might be very difficult to get stable. So basically, if you're buying this motherboard, I would recommend that you, like, depends on how you look at it, right? Obviously, if you buy a memory kit rated for 7600 and your CPU is good enough to run it at 7600, your life will be much easier. But if you buy a memory kit rated for 7600 and your CPU is a potato that just struggles to hit 7200, and those do exist, I have one of them, you're going to feel really bad about overspending on your memory kit. So I would not recommend, like, I basically, Gigabyte is being very optimistic with that QVL rating. I'm sure there are CPUs out there and memory kits out there that on this board will do 7600. I would also like not recommend that you like it's not even close to guaranteed that it's going to work in my experience. So if you're buying this board, I would say 7200 is really about as high as you would want to go. And it is worth noting that like you can buy Hynix A-die based kits at like DDR5 6000 these days, because Hynix A-die is starting to replace M-die just across the board. So even if you buy a kit rated for like 6000 or 6200, 6400, there's a very good chance you're going to end up with a Hynix A-die based kit, and you'll probably still be able to hit like 7200 or even 7000, 7200, something like that. And if you get lucky with your CPU, you might be able to do more than that. But Gigabyte's QVL, in my opinion, is being very optimistic. Because, this is very high for a 6-layer daisy chain motherboard. And actually, like, this is honestly kind of high even for like 8-layer daisy chains in my experience. So I don't know how many CPUs they got this to work with, but yeah, I wouldn't count on this if I were you. As for how does this topology compare to other 6-layer daisy chains, I don't know. I don't have any other Z790 motherboards that would have a I actually don't know how this compares to any of the motherboards in this price range, because I don't have any of them to compare. So yeah, that's the thing. So that's... Oh, and I guess, yeah, also don't go, like, if you're thinking of running higher memory capacities, like 64 gigs, because this is a daisy chain, go for a 1 DIMM per channel configuration, right? Don't buy a memory kit with, don't buy 4 sticks of DDR5. Generally ill-advised. Though with 13th gen, you might actually be able to do like 6000 plus on 4 sticks of memory. Especially if you're using a board like this, I wouldn't recommend it. If you're going to go for 64 gigs, you're going to want like 2x32. I don't know what kinds of speeds you can expect to hit, because I don't actually have any 32 gig kits. And with 2x16, yeah, even 7200 on this board can be quite a struggle, depending on how unlucky you get with your CPU. So anyway, that's actually it for this board. And honestly, like, I like it. Solid rear I/O. You get the safe boot button, which, you know, which, considering how difficult it might be to stabilize the memory, the safe boot button will be very helpful. And you do get a ton of like connectivity options, which is just standard. Like, I would almost consider it, that's basically standard for Z790. So I don't know if I would necessarily count that as a feature of this motherboard, though I've not looked too hard if like other motherboards in this price range are significantly worse. And the VRM can totally deal with a 13900K, just make sure you have some airflow, because the power plane likes to get quite hot, considering, again, that this is a 6-layer PCB. So yeah, that's the Z790 Aorus Elite AX. Thank you to Gigabyte for sending this board over. And that's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store, where you can pick up shirts, hoodies, posters, and, you know, like other, the usual YouTuber merch. There's a link for that down in the description. And I've also got a Bandcamp. If you'd like to check that out, there's a link to that down in the description below as well. And that's it for the video. So thank you for watching, and goodbye.